Hello everyone, in this video I'm going to explain one of the most important algorithm in the artificial intelligence area, which is the local search and optimization. So this includes HillClimbing, simulated annealing, and genetic algorithm. So in our century, artificial intelligence is developing how we solve the complex problems and make decisions. One of the crucial aspects of the artificial intelligence is the local search algorithm, which we explain in this video, which play a very significant role in defining optimal solutions in various domains. So let us start. So our outline is start with the local search techniques and optimizations, which is a HillClimbing, gradient methods, simulated annealing, genetic algorithms, and issues with the local search. So what is the local search exactly? So local search are the class of the optimization algorithm that explores the solution space by iteratively moving from the one solution to neighboring solution in a hope of finding an optimal or satisfactory solution, which means like we will go through the every steps by iterative method using, and at the same time we will explore the neighbors of it in order to find the very optimal and the solution that we satisfy. These algorithms are particularly useful when the entire search space is too large to explore all of the things. So local search always keep track of the single current state, move only to neighboring states, and ignore the paths. So the advantages is use very little memory and can often find a reasonable solution in a large or infinite continuous state space. And at the same time, there is a problems, which is a poor optimization. All states have an objective function. Goal is to find a state with the max or min objective value does not quite fit into the path. So we will solve some of the other local search algorithm problems with the using TSP algorithm, which is a traveling salesman problem. So what is the travel salesman problem? Travel salesman problem is a classic optimization problem in which a salesman is tasked with finding the shortest possible route that visit a set of the cities exactly once and returns to the starting city. TSP is an NLP hard, meaning that finding an exact solution for the large instances becomes computationally infeasible. So this is the brute force. We can use the brute force, which means like we will explore all the place using the all generation, using all the ways in order to find the local, in order to find the global and optimal solutions. So using nearest neighbor algorithms starts from a randomly selected city and repeatedly chooses the nearest unvisited city until all cities are visited. Simple and fast, but it may not always produce the optimal solution. So and there is some algorithm that use TSP, which is simulated annealing, and genetic algorithms, which we'll explore in the last of the video. Now our first algorithm that we use, the HillClimbing. So what is the HillClimbing algorithm? HillClimbing algorithm is the straightforward local search algorithm that starts with the initial solution and iteratively moves to the best neighboring solution that improves the objective function. Here is how it works. First, it will begin with the initial solution, often generated randomly or using the heuristic method. Evaluation. Calculate the quality of the initial solution using the objective functions, which means it will calculate the using the fitness, evaluate the state, is it good or not, if it's closer or not, and after that it will visit to the unvisited site. After that, it will limitation to get stuck in a local optima, which are the solution that are better than their neighbors, but not necessarily best overall the solution. To overcome this limitation, HillClimbing algorithm having developed such a stochastic hill climbing and simulated annealing. So using this is the in this slide we are showing the pseudo code of the hill climbing with the using TSP. So local variables, current node, neighbor node, and it will go to the iteratively, as I said, like in hill climbing. So right now this is the P source that we use, and the other source is related and from the GitHub code, which is IMA Python. This is the P source of it. Right now I'm going to show the Python code that has been written to the HillClimb implementation. So here we're going to the our hill climbing. This is the our driver code, which will explain. So when I run it, first of all, it will sort all the cities, like which is all cities after the sorting. So this is all the cities, and after that, it will use the hill climbing algorithm with the TSP, which is a travel salesman problem algorithm, and after that, it will show us some visual places like which is it will start with this one, which is cities and y coordinate, and this is the optimal tour, like which means like it will visit all the neighbors that it have, like from here, there, from there. This visualization was done with using this matplotlib algorithm and some visual algorithms. So this is the optimal tour. So there is some points that I want to explain about our code. Like our code used the Romanian map, like which is the all cities of the country Romania, like with the some points of it, like how it goes, like the goal states that we have. So it will use undirected graph with the using the dictionary implementation with the node system, and it will use the travel salesman problem, which was implemented here, like that it have the two opt, it is a neighbor generating function for travel salesman problem, like the here our to opt function will generate the neighbor travels, like neighbor generates for the TCP problem, and it has the actions which can be executed in a given state, and it have a result like after applying the given action on the given state. And at the same time it has a path cost, like it will total distance for the travel salesman to be covered in its state 2. So this is the visualization in order to understand for all the users that what's happening, like it will print out or it will display the optimal tour with the x and y coordinate of the cities, and it will draw like blue lines for the optimal tour in order to understand. And this is the main problem that we have, like which will inherit with we can say is it's the abstract class for the formal problem, like we can use in the subclass like a goal test and path test, and that will create the instance of our subclass and solve the various search functions, like let's say like it have the goal test which can be used in our TCP problem, like default method compares to the states to self goal and for the self goal at the same time. And this is our algorithm by itself, which is like a hill climbing problem with the which starts with the empty list with the neighbors, and at the same time every time when it explores the neighbors of itself, it will append to this list, and after that it will display, like which means like it will iterate like 10,000 times in our list, and in order to find the local optima, or we can say the local or optimal solution. So this is the all of the code. This is driver code, and we have a node which we will use in our TCP or the will in the hill climbing problem. So and the Romanian map, it will sort like which we seen our display. That's all for the hill climbing problem. So the second problem that we want to explore is the, as we can say, for this one, which is a simulated annealing. We want to talk about a simulated annealing. So what is a simulated annealing? It's the probabilistic local search algorithm inspired by the annealing process in the methodology. It allows the algorithm to accept the worst solution with a certain probability which decrease over time. The randomness introduce exploration into the search process, like helping the algorithm escape the local optima and potentially find the global optima, like which started the initial solution, generate the neighboring solution, choose a neighboring solution based on the improvement in the objective function, continue iterating until it terminate the condition. So did a simulated annealing is like a physics inspired twist on the random walk, as we can say, and the interpretation, like imagine letting a ball roll downhill on the function surface. It's like a hill climbing for minimization. So this is the our pseudo code that we use for the simulated annealing, like which is we input a problem at the same time, and we will go to the node and the next node, and we'll use the temperature in order to control the probability of the downward steps. So we will go to the loop which will iterate through in order to find out everything. So this is the temperature, like if the high temperature, which means like it's locally bad move, is the higher. If it's low temperature, is probability of the locally bad move is the lower. Typically T is decreased as the algorithm run through. So this is the P source that we use it in our I'm a Python GitHub code which was provided. So right now let's go to the code that we use with to our simulated. So we use a Gaussian kernel, which is generate a 2D Gaussian kernel using the Gaussian function with the mathematical functions, and at the same time we use the pick a finding problem, like which has the initial grids, like which will implement the grid functions, like and at the same time it has a value which element is given the state, and it has a neighboring state which give us the neighbors as the hill climb that we did, and at the same time it will find a fig in the grid using the simple algorithm. So this is that we have a two driver codes, which is we use the 8 directions with the using 8 direction and 4 directions. So let me test the code, which is import the Gaussian kernel and using the picky finding problems. When I run this code, it need give us the 2D Gaussian kernel in the display, and at the same time it will give us the heat map, which we need to be explained at the same time, like which have 2D from here, the x coordinate and the y coordinate. So this is for the 4D function which we have. So let me check with the 8D. Like when we check with the 8D function, it will go this the which we call it the main frame. It will go to the corner of that, like with the 30 25, and as you see it's increased from the x coordinate, and it went to the corner side of that. So as we see, this is the displacement, and it is the explanation of the simulated annealing. So the third algorithm that we want to explain and that we want to go through is the our like which is call it simulated annealing, is for a genetic algorithm. As we know, genetic algorithms are inspired by natural evolution and particularly used in optimization and search problem like a large state, which in a initialized random population calculate the population fitness, selecting individuals for matting the new populations at the same time. So this is some visualization, like we want to go through, like every time it will create a generation crossover, and it will mutate until getting the local and until getting the answer for that, and it should, at the same time it will go to the new states, like we can use with the states for four state, two pairs of the two state randomly selected, and that's it for that. And this is the source of the our p source algorithm, which can be used, and which was done, which was getting from the GitHub. So let me go to the code through. So this is a genetic algorithm. We have this, it will ask you which encodes the codes, like we have in our the population, and it will go to the 100 population, and it has a mutation rate like 0.7, and it has a driver code here, which is we will run through after a couple of minutes. So this is the we use the stepwise, which go through the generation at the same time with the fitness fitness, and after that it will go to the some init population function. So let me run the driver code. So when we run, we see this is our list, and after that it's merging using the split function. At the same time, right now it's going through our iteration part, which will go from there, and it will show the answer for us with using the display output function. So it will like wait a little seconds. So as you see, this current best is genetic algorithm. It went through the generation 932 times, and it goes through the fitness 20 times, which is the most important part of the algorithm, which goes through in the generation inside of the function. So using this generation, it went and it gave us this result with a genetic algorithm. And that's the end of the overcode. Thank you so much.